Hello! The video you are viewing is part of a series that will illustrate a number of critical topics in the field of materials science, ranging from sample preparation to XRD. The laboratory procedures used to demonstrate each topic will also be discussed in detail, so that curious viewers may know how to replicate each experiment, should they choose to do so. This particular presentation concerns cold working of cartridge brass at Arizona State University in MSE 421 during the spring semester of 2017. Group members consist of Tayler Fulton, Dominic Randall, Ezequiel Nunez, and Jorgen Hansen. We'll begin this presentation by discussing the background of the cold working process. Cold working, also known as strain hardening or work hardening, is a technique used to determine the strengths of a material through plastic deformation. This technique can be useful in hardening and strengthening of a metal alloy. The cold working process is characterized by working below the material's recrystallization temperature, which is the temperature above which the effects of strain hardening are eliminated during annealing. This process of plastically deforming an alloy can increase dislocation density by orders of magnitude, sometimes from 10 to the 6th centimeter per centimeter cubed to 10 to the 12th centimeter per centimeter cubed. The main takeaway is that ductility will decrease and grain boundary density will increase as a result of cold working. Next, we're going to talk a little bit about the mechanism behind cold working. At a microscopic level, working the metal will cause grain boundaries to be distorted in the direction of the rolling, which nucleates dislocations. This nucleation and growth of dislocation will impede further movement of the dislocations and therefore increase the strength of the material. Think of it like a packed concert. It's much harder to get to the stage when you have to push through a dense crowd of people. Also, the percent thickness reduction of the sample being tested can be used to estimate the percent of cold work. This slide shows how cold working is actually performed during this experiment. The picture on the left shows a side view of the cold working tool used in this experiment, also known as a cold roller. This process is fairly simple, and the only things that are adjusted are the height of the roller and the angle of tilt. Later in this presentation, it will be shown how these parameters are altered by the user. The image on the right shows what occurs in the microstructure due to cold working. The figure resembles the brass sample being fed through the roller, shown in the image on the left. The new grains, which gain a new structure, as you can see, are elongated and become smaller. The thickness of the material will decrease and the length will increase. The width will remain relatively unchanged. The purpose of this experiment is to have students familiarize themselves with the concept of cold working as well as the process. Students will also learn how to conduct Vickers hardness testing, which provides valuable information about properties like ductility, yield strength, fracture toughness, and plastic deformation resistance of the sample in question. Using a cartridge brass sample, cold working will be demonstrated by finding a relationship between cold work percentage and hardness. It was mentioned earlier in the presentation that the thickness of the sample could be used to calculate percentage cold work. But percentage cold work can be calculated in two different ways. First, the cross-sectional areas can be used. The initial area minus the final area divided by the initial area times 100 will give you percent cold work. The thickness of the sample can only be used if sample width change is negligible. This slide shows a very general overview of the lab procedure and goals for the experiment. First, we will establish a sample baseline for the cartridge brass sample. This involves obtaining dimensions of the sample, the initial microstructure, cleaning the sample, and taking an initial hardness measurement. This sample will then be cold worked in uniform increments. A hardness will be obtained for each level of cold work, and the dimensions will be obtained at each level of cold work. Finally, this data will be analyzed. The first step of this experiment was to establish a baseline against which the cold work sample could be compared. A baseline allows us to see what effect the cold work has on the brass sample. Annealing the sample is critical to this baseline because it removes dislocations. One of the goals of this experiment is to see how cold working affects the microstructure of the sample. Minimizing existing dislocations before cold working means that we can safely assume any dislocations observed in the microstructure after the cold working procedure are purely a result of the cold working process. Next, we measured the length, width, and thickness using calipers. Initial dimensions of the sample were approximately 2 inches by 1/4 inch by 1/8 of an inch for this experiment. Average dimensions were used, and they help account for uncertainty in the dimension measurements. It was also necessary to clean the sample. The sample was rinsed with dilute nitric acid, which removes oxide layers that obscure the microstructure and affect thickness measurement. In this slide, we will talk about operation of the cold rolling machine. Cold work occurred in approximately 10% increments. Percent cold work was determined by the area of the brass sample. Final and initial areas were used in this calculation for each level of cold work. The sample was cold worked from 0 to 60%. It should be noted that the thickness of the sample should not fall below 1/16 inches, or viable Vickers hardness testing data would not be able to be obtained. It was also observed that sample length increased and thickness decreased, but width only increased by 0.9 millimeters. This relatively negligible increase in width indicates that the thickness before and after cold working can be used to calculate the percent cold work. When operating the machine, the sample was fed through the roller using a long object to prevent injury. Adjusting the wheel and gear assembly is how the height of the wheel and angles are changed. Moving the wheel lower corresponds to a greater cold work because the sample is being compressed more by the roller.
There's a red button over this side as well. So this thing was elongated by somebody. If it's not going through, then we can bring it up a little bit.
This slide describes the hardness testing procedure that was used at each level of cold work. Hardness measurements were obtained using a Vickers testing machine. The procedure began with the user placing the sample on the observation deck of the machine. The user then switched to the diamond indenting head which was used to make a notch in the sample through the machine's automated process. The user then switches back to the microscope and finds the diamond-shaped notch that the machine has made in the brass sample. As shown in the images on the right side of the slide, the user aligns the crosshair and line with the leftmost edge of the notch and slowly moves the line to the rightmost edge by turning the knob on the eyepiece of the machine. The user then records the value corresponding to the number of knob turns, one full turn equals 50 in this case, and enters this value on the keypad. This process is repeated after rotating the eyepiece to the vertical orientation. When the average of the hardness values provided by the machine were used, these average values help reduce experimental error. It is important to heed manufacturer instructions when indenting the sample. You don't want to damage the microscope by forgetting to switch to the indenting head before starting the indenting process. Next, the data analysis of the experiment will be discussed. Hardness values were plotted against cold work in Excel to yield a positively sloping linear trend and an equation that reflects this trend. The positive linear relationship between % cold work and hardness can be seen in the plotted data. As % cold work increases, sample hardness increases. In addition to a linear plot, 3 other graphs were also generated. Going clockwise around the slide, linear % cold work and log hardness, log % cold work and linear hardness, and log % cold work and log hardness. All plots show that hardness increases as cold work increases, with generally positive trends. These results support the idea that dislocation density increases with more cold working. Finally, the expectations and conclusions of this lab will be discussed. It was expected that cold working would increase dislocation density. Greater dislocation density means that dislocations cannot move past each other. The lack of dislocation movement contributed to greater hardness in brass cartridge samples. The results of our experiment match these expectations, with hardness increasing as cold work increases. Cold working affects the mechanical properties of metals. Understanding these property changes can help engineers more effectively use cold work materials in the design process. Students were able to learn and understand the concepts involved with cold working. Processing materials through this technique will increase strength and reduce ductility. This means that cold working should be used with caution. If a material is more brittle due to cold work, it can lead to critical failure if a particular structure was designed with plastic deformation in mind.